Hello, everyone. So we're going to talk about the our last sorting algorithm. It's just simple sort. Okay, so a simple sort is a very, very simple one to kind of do. I suppose the best way to use to show it you. Okay, let's pick some numbers: 3, 5, 1, 2, and 4. Simple sort literally just finds the minimum element in the array or the list or wherever you're looking at and places it at the beginning. Okay, so it'll run through the array, it'll find the one, and it puts it at the beginning. Okay, so now we've got 1, 5, 3, 2, and 4. Okay, so that's after the first pass. Okay, simple as that. Now we'll go to the second pass. Okay, it finds the minimum, next minimum. Okay, 2, puts it in the correct spot. So there's after the second pass. After the third pass, so it's got those two. So it'll find a 3 and puts it in the correct order. Finds the next one. And that's it done. Okay. So literally just finding the smallest one, putting it in the right spot, and swapping. That's all it's doing each time. Okay. Simple sort, as the man says. Okay. Now, what I'm going to do is I'm going to go through all of them again. I'm going to go through the bubble, the insertion, the quick, the simple, then the two searches, the binary and the linear. And then we're going to talk about something that's called complexity. Okay, so this is probably where it gets into the real honors kind of end of it. So I'm going to use a set of playing cards just quickly to go through. We'll go through bubble sort first of all, an ace. We'll get one more in. Okay. So we're going to do a bubble sort on this one. So we're going to count an ace as a 1. Okay, so we look at it first of all, what we should, at the end of our first pass, we should have a king on the right-hand side. Doesn't make a difference where anyone else is, but a king should be on the right side with a bubble sort. Okay, so if you remember what a bubble sort does, it looks at pairs and looks at sequential pairs. So it looks at this pairs and then it sorts them smallest to biggest. Okay, then looks at this pair, smallest to biggest, smallest to biggest, looks at this pair, smallest to biggest, looks at this pair, smallest to biggest. So as we said, at the end of the first pass, we should have a king. So that means at the end of the second pass, we should have a queen. So let's have a look at that. It looks at the first pair, no swapsies. It looks at the second pair. Sorry, looks at the first pair. Yes, there is a swap. The ace is a 1, what we said it was going to run. Looks at the second pair, no swapsies. Third pair, yes, there's a swap. Fourth, there's a swap. Fifth, there's no swap. That's the second pass. We have the queen where it's meant to be. Okay, now let's look at the third swap. No, yes, no, no, no. Now you'd think it stops there, no, but it runs through it once more. No, 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 done. Okay, so that's it done. That's your bubble sort done. Now let's have a look at it in terms of its complexity. What does it mean? Okay. The best case scenario, the absolute best case scenario is it will do it in 1, 2, 3, 4, 5, in 6. So its best case scenario is it does it in n times. Okay. However, its average is a quadratic, it's n squared. And obviously the worst case scenario will also be n squared. Okay, now both of these things, and we'll see this as we go down, the notation for them is called big O. okay? And the best case scenario has a omega. That's the symbol for them, okay? But big O is the one that any computer scientist will always talk about, the big O, and they're always really looking at these two. Never really looking at the best. They're always looking for the worst and the average, because that's how complex the time needs are to get to it, okay? So in best case scenario, get it in whatever, 5 or 6. Worst case scenario, you get it in 36 passes, depending on the complexity, okay? So that's for bubble. Now we're going to have a look at insertion. Let's have a look at the insertion. So remember, insertion looks at the second one, compares it to the first one, then the third one compared to the second and the first and the fourth, and then inserts it in the correct spot. So it's going to have a look at this one, and it's going to see, well, is the king bigger than an 8? If it is, it's in the right spot, so we'll move on. Is the queen bigger than the king? No, it's not, so insert it in the right spot before it. Is the jack bigger than the, so no, you insert it in the right spot, okay? Is the ace? No. Where does it go? It's inserted in the right spot. And is the 7? No, it's not. You insert it in the right spot, okay? So you can see that, look, that even just doing that looked a little bit quicker. And it is true. With an insertion, okay, the best case scenario for an insertion is the same. It's actually an n, okay? The average for an insertion is an n squared, complexity of big O, and the worst is also n squared, okay? So in reality, it does work a little bit better than a bubble, tiny way better than a bubble, but in terms of the maths of it, in terms of the complexity of it, it's exactly the same in terms of its complexity. These are all the most basic types of algorithms, okay? So the next one we're going to have a look at is a simple sort. Sorry. So a simple sort, I suppose, and the simple sort, we just kind of look at it, okay? So the idea of a simple sort, you go and you find the smallest, okay, and you replace it at the start. Okay, you find the next smallest, and you replace it. You find the next smallest, it's there. You find the next smallest, and you replace it, and then you're done. Okay, and again, you can see it's the same idea. The best case scenario, it'll be done in n times. The average is n squared, and the worst is also n squared. So these three have the same kind of idea, okay? They have the same idea on it, okay? Now you're thinking, well, why did you show me them? Well, they're the three most simple types of sorting algorithms you can possibly have. And it's reflected in the complexity of how long it takes to do n amount of them, okay? Now let's go on to the other sorting algorithm we had, which was the quick sort. So I'm going to use a few more here, make it a bit easier. So what's the idea with the quick sort? Quick sort looks for a pivot point. We're going to pivot always around the end one, which is the 7. So if you bear with me just a couple of seconds. Let's see, can I get this to... Right, so hopefully that gives you a better kind of view of everything, okay? Now, we're going to pivot around the 7. So we take the 7, okay, and we move the 7 to its pivot position. So how do we pivot? Well, we then tell the computer everything that is less than 7 will go on the left-hand side, and everything that's the right or bigger than 7 will go on the right-hand side. So we're differentiating with this being the pivot point. So going through it, that's greater than, so it's going here. Less than is going here. Greater than is going here. Less than is going here. Greater than is going here. And less than is going here. So I'm going to leave him there. Let's move them up so everyone can see it. Okay. Now we start pivoting again. So let's pivot on this side first because it's an easier one to do. We always pivot with the last element in the list. So we put everything smaller than an ace on the left, anything bigger on the right. So the only thing I have is the one on the right. And suddenly they're done. You can see that. Now let's pivot the ones on the right. We're pivoting around the ace or the queen of clubs. Anything less to the left. So I have an 8 and a jack. Anything greater on the right, a king. Okay. So pivot again, nothing there. So boom. They're done. Now pivot around this fella. Anything less goes on the left, anything bigger on the right, they're done. Pop them back in. Now, it looks more complicated, and it is more complicated. It is not like the other ones. It's not a simple one. However, that's reflected. That is reflected that in its best, it's n times log to the base 2n. Okay? Its average is also n log to the base 2n, and its worst is like everything else, is n squared. Now, you think to yourself, well, what does this mean? Okay? Well, let's say you have 32. That's 32 by log to the base 2 of 32. Okay? That's the maximum number of times you'd have to actually run through that to get it. Okay? If it's 64, it's 64 log to the base 2 of 64. And again, if you put into your calculator, these are not big amounts. Okay? They're a lot smaller than you would think. Okay? So quicksort is a lot better even on its average than any of the others, hence the reason it's used a lot. Okay, now we'll have a look at the two searches and see what they look like in terms of their complexity. Okay, so let's do let's do the linear search first of all. Linear search, if you remember, if I want to find the queen, not 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 the queen, queen. That took me 1, 2, 3, 4, 5, 6, 7. So for a linear search, for a simple sort, the worst case scenario is it's going to be for best case scenario is going to be n. The average is going to be n, and the worst is n squared. Sorry, my bad. I'm just out there looking at the wrong one there. Sorry, for a linear search, the best case scenario is actually 1. For example, I'm looking for a jack. Let's start the algorithm. Oh, found it on the first go. So that's the best case scenario. Okay. The worst case scenario is actually going to be n. There's no average. Sorry. So the best case scenario, you find it on the first go. The worst case scenario, you have to get to the right to the end to find it. So for example, if I ask you to do a linear search on the alphabet and I want you to find A, the best case scenario is you find it at the beginning of the alphabet and you're done after the first one. The worst case scenario is 26. In other words, I want you to find a Z. You have to go right to the end to find it because you have to check everyone between them. Okay? Now, the last one, the binary search. binary search. The only thing about a binary search, it has to be in order. Okay, so what we'll do is we actually won't put them in order, and we will sort them and then search them. So I'm going to put these in order, and then I'm going to find 4. Okay, I'm going to find the 4 after I put them in order. Okay, so first, let's put them in order. So you can use any of the different sort algorithms to put them in order. I'm just going to use bubble because I like it. Okay, so bubble means you check now, if I'm sorted, I want to find 4. 4 means that I need to look for the median value. 1, 2, 3, 4, 5, 6, 7. The median value is 8. Binary search says any number less, if the number you want is less than 8, you ignore everything above. So suddenly, they're all gone. Binary search says find the middle number. If it's the middle number, you're sorted. If not, ignore bigger or smaller. Found the 4. So then it took me 2 steps. See how quick that is for that search compared to the other one. So what does that mean in terms of the complexity? Well, for a binary search, the best result, like any other search result, is 1. You find it on the first go. Okay? The worst result is just log to the base 2 of n. Okay? So you'll actually find it's because you're splitting in half each time, you know, it's a base 2. So if half, a quarter, a 16th, you will find it fairly quickly. In fact, if you have something like a million search elements in a list, and if you use a binary search, the worst possibility is you get it after 30 possible answers. You can play this game. You can ask someone to pick a number between 1 and a million. And you can guess, if you guess halfway, so if you pick like 700,000, I say, is it bigger or less than 500,000? They say bigger. Well, then that's 1 go gone. Then is it bigger or less than 750,000? That's 2 goes gone. Is it bigger or less than, you know, that type of way. You'll get it within, you'll probably get it in less than 30 goes, but you'll definitely get it within 30 goes. It's amazing. Okay, so there's a quick going on it. What I might do is, hopefully when we get back in, we'll have another touch on this. So I suppose to bring it all back together, the big O notation deals with the complexity of finding a number in a list of size n. So find any number in a list of n numbers. Okay, that's your big O. And we really want to just focus on these ones, the average and the worst case scenario. A lot of the best case scenarios are just, you know, easy enough to remember. Okay, right. Best of luck and thank you.